lots of your brain. You have to use a lot of your brain resources in order to understand the system. So in the context of this talk, we are going to talk only about system complexity. I'm not pretending that data-oriented programming helps to reduce computational complexity. It only helps to reduce system complexity. In other words, it makes our program easier to understand. And maybe you know this quote from the great book, SICP, Structure and Interpretation of Computer Programs, where they have this great insight that program must be written first for other people to read and not only for machine to execute. And in today's cloud era, it's even more relevant because let's say a program has a performance issue, no problem. You double the scale of your Amazon instance and the performance issue is gone. But if your program has a complexity issue and it makes harder for developer to add new features, it won't help you to add twice more developers. First of all, it costs a lot, but it's not sure that two developers working on the same feature, if the system is complex, they will be able to solve the problem in a shorter time. So it's very important to put an emphasis on when I'm writing code or when I'm choosing a technology, not only how fast I can write my program, but how easy it will be for other developers to read my program. And you know, sometimes other developers is me in a month. How often it happens that I cannot read the code I wrote by myself a month ago because it's too complex. So data-oriented programming will help us to write programs that are easier to read and to maintain, that are less complex. Okay, and it's a paradigm that helps reduce complexity, not of every program. It's on a very specific set of programs, what I call information systems. Basically, an information system is a system made of multiple programs that deal with information, a front end, a back end, a data pipeline. You fetch data from the database, you change a bit the shape of the data, you pass it to another service. This service gathers data from multiple sources, merge together, filter, send back over the wire on JSON to a front-end application that treats the data, the user interacts with the data, data is sent back to the backend, to another backend, to a pipeline, it's stored in a database, etc., etc., etc. So information is processed as data by multiple programs. What would be an example of a kind of program that doesn't fit? For example, if you want to write a compiler. When you write a compiler, you have a clear input and a clear output. The data starts that you use, you create, the program creates the data, and that's it. Or if you want to write a game engine, you don't need to fetch data from somewhere. The data belongs to you. So when the data does not belong to you, to the program, then my claim is that data-oriented programming is helpful to write less complex programs. Any questions so far? Is that clear?
Yes.
Okay, perfect. Let's continue. Okay, great. And the interesting thing is that, in a sense, data-oriented programming is not something new. When I wrote the book, in order to write the book, I didn't have to invent anything. I just had to gather best practices that come from various languages. And I met all those principles and best practices in Clojure. So Clojure is a language that really embraces data-oriented programming. And the language almost forces you as a developer to apply, to adhere to the principles. But the principles themselves have nothing to do with Clojure, the language, and the syntax, the Lisp syntax of Clojure. It's principles that are applicable to almost any programming language. And my goal today is to share with you those principles so that you can apply them to your program, whether you code in JavaScript, Java, Python, C#, Ruby, Go, whatever, you name it. So what are those principles? If I were to put an advertisement, one word or one sentence advertisement, it would be treat data as a value. In the same way that in almost every programming language that we have today, numbers are values, strings are values, and we can easily manipulate them in our programs. In data-oriented programming, help us to have the same relationships with data, that it feels natural to manipulate data. For example, when something is a value, it's immutable. A number is immutable. A string is immutable. And the same in data-oriented programming, we are going to see that data is immutable. Another aspect of it is that numbers exist on their own. Even in Java, you don't need an object to wrap a number. So the same, in data-oriented programming, we are going to claim that it's better to have data separated from code, behavior, business logic, so that we can interact with data on its own. And we will see other examples of this meta principle. So now that we have seen the meta principle, let's see how it expresses itself into four basic principles that are language agnostic. Number one, we separate code from data. We don't encapsulate data inside objects that manipulate the data. Number two, we represent data with generic data structures. We don't create a custom data types per data. One data type for a user, one data type for a customer, one data type for an enriched user, one data type for a VIP customer. No, we use generic data structures, mainly hash maps, to represent our data. Number three, we never ever mutate data. As I said before, data is a value. Like a number, when you have the number 42 and you add 1, you get 43, but 42 has not changed. The same, you have a hash map, you want to add a new value, fine. You create a new map with the added value, the additional field. And we will see how to make it in an efficient way so that you don't have to always deep clone. Number four, we separate from data schema and data representation. Data lives on its own, like a number. When you create a number, you don't say, I create a number that is comprised between 10 and 15, or an age that is comprised between 0 and 120, or something like that. You create a number, and somewhere else in your code, you use a different construct to express the constraints that you'd like to check on data, on the number. And we are going to take the same approach in data-oriented programming, and we are going to separate between data and data schema. Just a moment, it's getting old, hot here. Okay, now let's drill down into each of those four principles. Have you ever thought about, let's say, in object-oriented programming, Java or C# or C++? What makes a system complex? So let me give you an example. Imagine a digital library when you can borrow books. Books have authors, you have users, you have members, you have librarians, you have many kinds of entities. And more or less, you would build your system around objects, and you would have kind of a class diagram like the one on the screen. So you'd have a library, a catalog, user, librarian, book, author, book item, book lending, member, and more and more and more and more. And quite quickly, the system becomes complex. What do I mean by that? There are lots of interactions between the classes. Look, for example, at the librarian. The librarian inherits from user. The librarian is associated with library. The catalog uses librarian. Librarian uses book lending, etc., etc., etc. And it makes all those interactions, like in a human system, the more interaction you have, the more complex the system is. And when you want to understand what's going on with librarian, quite often you have to understand what's going on with the catalog. And if you want to change something here, you are scared that you might have broken something in another place because everything is intertwined and connected in various kinds of relations. I'm not an UML expert, but from what I remember, you have association, you have composition, you have inheritance, you have usage, and all the classes are intertwined and interacting together, and it makes the system complex. So what can we do? We split code and from data. How does it look like? It depends on what programming language you use. If you are, let's start with the code. If you are in the object-oriented programming language like Java or C#, you will probably have classes with static methods, but no members. If you are in a more functional language, you would use stateless functions. What about data? You choose. You can either use classes with only members, no code. You have data records, or you could use string maps also. It doesn't matter. The moment you separate the code from the data, the system gets simpler. And I'm going to show you why in a moment. So let's start with data. Here I'm using JavaScript as a pseudocode language so that we can all be on the same page. If there is something not clear, let me know. So imagine I want to represent a book in my digital library. What I would do, I would create a class named book that has only data members. You see, no code. Title, publication year. That's it. Another option is to use a record. In Java 14, I think they have added this thing called the data record. It's the same, but less verbose syntax. Or you could use a string map in JavaScript, for example. This is how I would represent a book. And what about the code? You have two options, either with classes and static methods, again, in JavaScript. You see, it's a static method. It doesn't have access to this or self. It receives the book as an argument. For example, here, a method that calculates the book info, calculate. Return the string with the book info, with the name of the book, was published in, and the publication year. And you can also use functions. So it doesn't matter. You don't have to be, if you prefer the OOP style, go for it. If you prefer the FP style, go for it. What's important is that the functions are stateless. They don't have an implicit dependency on a this parameter or on a self parameter, on something in the lexical scope. All the arguments are explicit. And this is what I mean by stateless functions or static methods. And why does it make the system less complex? Look at the magic that happened here. I took the exact same system that we had before here on the left, and every class, I split it into two classes. One for the code, one for the data. For example, library code, library data. User, oh, I missed this one. User code somewhere. No, user, no, because it was just a base class. Catalog code, catalog data. Librarian code, librarian data. And look at this magic. Do you agree that the system on the right is less complex than the system on the left? There are much less interactions between the nodes. The librarian node that was involved before in 7 interactions now has only 1, 2, 3, 4 here, and here only 1. And it's not a surprise when you think about it. If you have split each class into 2, so part of the relationships are now with the code, and part of the relationship are with the data. So we have more nodes, but less relationships. And the system is less complex. If you want to understand what's going on with the book data, you don't need to bother yourself with what's going on with the book code. If you want to understand how the librarian code works, you don't need to bother yourself with the librarian data. You have less dependencies. Okay, so that was principle number 1. And if you take only one thing from this talk, it's already, I think, a good benefit. It will make your application simpler. If you take some classes of your program split between code and data, make the code stateless, data with no code, you will see an increase or a reduction of complexity. But we can move forward. And again, it has been done. People have not waited for my book to do that. People do that. I think most Java experts with a lot of experience, they apply this principle. Okay. Second principle is about how to represent data. And because we want to treat data as a value, we want to be able to represent data with generic data structures and not only custom types. And you can use a map constructor, for example, in JavaScript, where you pass a list of tuples with the keys and the values. Or you could use the map literals that is available in some languages and not available in other languages. So in JavaScript, Ruby, Python, etc., you have the map literal. In Java, you don't have the map literal. You have to use the map constructor. But that's a bit cumbersome, but it works. Okay, and why is it beneficial in terms of complexity reduction? Because now, instead of this diagram made of two sub-diagrams, what we have, in fact, is a single diagram. This diagram of the relationships between data is not anymore present in the code. It's present more in our head and in the data model. It's life, you know. The fact that in a library you have a catalog, it's a fact. You cannot change that. It's part of the business. It's not part of the code. But the fact that in my code, in order to instantiate the library data, I have to require the definition of the catalog data, that's my problem as a programmer. And the moment we use generic data structures to represent data, we can get rid of all this complexity. We don't need anymore to let our compiler know about the relationships between various entities. In other words, there is a weak dependency or between code and data. It's not anymore a strong dependency. It's a weak dependency. And it allows to have loose coupling between components. For example, a component could create a catalog data and send it to another component without having to import the component definition. Whereas in object-oriented programming, the traditional way, where everything is represented with classes or records, even in order to create data, you have to import the definition of the data. And another benefit, the data model is more flexible. Let's say you have a book with a title and a publication year. And in some use case, you want to add another field, like the ISBN of the book or the color of the book cover, something like that. For whatever reason, you are not forced to create a new class or a new type for this kind of books. You can just add the field on the fly. If you want to send over the wire to translate to JSON, usually when you have custom data types, it's complicated. You have to do reflection, you have to use third-party libraries, you have to do lots of complicated things. When it's data, translating a hash map, a nested hash map, a very nested hash map into JSON is trivial. It's trivial. And because in information system, programs communicate over the wire, it's quite important to be able to easily serialize and deserialize data. Okay. In a sense, I don't know how you guys are.
Question regarding using generic data structures. Basically, when we move from like a user object to a hash map which stores user data, are we losing type safety? And if we are, then is that a trade-off?
Yes, yes. You lose type safety. It's a trade-off. And principle number 4 is going to mitigate this trade-off. Great question. So I don't know, you tell me, you are from India, from the East. I am from France, but I love meditation. I don't know if you guys are into meditation or yoga. Are you a meditator?
Yeah, we have meditation and yoga both.
You have, okay. So I'm going to tell you my take on meditation, but probably you know better than me. A big part of meditation is about being able to experience the world without the filters of our mind. And one big insight of meditation is that suffering has to do more with the way my mind sees the world than with the world itself. In the world itself, there is not so much suffering. Most of the suffering is created by our mind. And if I am brave enough to remove a bit the glasses or the filters of my mind and experience the world as it is, wow, if I can see a flower just as a flower, or I can smell the odor of a flower just as it is with no word, with no concept, it's a bliss, it's amazing. And even pain, if I can experience, let's say, physical pain without interpretation, why, what does it mean? I'm going to be sick, I cannot work today, Okay, so it's a pain. It's a bit painful, but it's much less painful than with all the projections that our mind adds on the reality. So my analogy is similar. For a program, reality is data. You cannot change data. It's part of the world. But once you add objects, it's like mind filters on reality. And quite often, the problems we have, the suffering we have in our programs, is not because data is complicated. It's because the objects we created are complicated. So data-oriented programming is a bit about removing the objects so that we can experience data directly. And sometimes it's scary. I'm losing a bit of safety, but it gives lots of freedom and flexibility. Okay. For example, when data is represented as data, so here I have data as I would write it on the blackboard, as it is in the real world, catalog, books, authors, an example of a book, Watchmen, example of authors, etc. If I represent it as data with generic data structure, I can visualize it. I can print my whole system data to the console. I can send it over the wire. I can save it on a file. I can serialize it very easily, as I said before. I can manipulate it with generic data manipulation functions. I don't need any custom function to manipulate data because it's just data. There is no need for reflection. It's just accessing fields in a map. And each piece of information is accessible via a path, like in XML or HTML. For example, the information path for the name of the author who has did Alan Moore is this array. And I can pass the array to a generic getter function and get back the value that is there in this path. I don't have to write any custom logic, any custom code. It just works because I represented data as data. Okay. Number 3, principle number 3 out of 4, we never ever mutate data. Never. And when it's the case, lots of bugs simply disappear, or even not disappear, don't emerge. Lots of thread safety concerns and mutexes and deadlocks, it's simply not there. That's part of the reason that it's so fun to work on a program that is that adhere to data-oriented principles. Values never change. A number will stay the same forever. You can create new numbers, you can calculate new numbers, but numbers never change. Values never change. Do you remember, I think at some point in Java, strings were mutable? It was a nightmare. And the moment they decided to make the strings immutable, many bugs just vanished in the air. Thread safe. Values are thread safe. You can send a number to a thread, no problem. You can send a piece of data to a thread, no problem. No side effects, only calculation. Okay, now the question is how? What about performance? If you don't mutate data, let's say you have a catalog with thousands of books and authors, and now you want to add a new book to the catalog, and you don't want to mutate the original catalog. How are you going to do that? You would have to deep clone the whole catalog and make a change? No, it will not be acceptable in terms of performance. Should I clone? Should I copy and write? And there are lots of strategies and tricks that people have created in order to deal with mutability. Maybe we need special data structures. So let me reveal you the secret. How does it work? How can you have two things together? Not mutate data and not having performance issue. And it has to do with structural sharing. So let's take an overview of our library data. So in the library, we have the catalog and the user management. User management, we have lots of stuff here. Imagine that instead of the 3 dots, you have millions of records for all the users. And in the catalog, we have the authors and we have the books. And again, in the author, we have tens of thousands of authors. And in the books, we have lots of books, and one of them is Watchmen. Okay. And now, let's say we want to change the publication year. I have a small mistake here. Let's say I want to change the publication year of Watchmen. I discovered a mistake. Instead of 1987, it should be 1986. How am I going to create a new version of the library that contains the change without mutating the library and without having to deep clone the library? It sounds like mission impossible, but it's doable. And here is the trick. It's called structural sharing. What I'm going to do is I will create a new library. The pink one is a new library. But as you will see, the vast majority of the data in this new library will be shared with the previous library. For example, user management is going to be exactly the same, and not by copying, just by pointing. So I will have a reference here inside the new library where the key user management will point to the value user management from the previous library. And this operation is for free, nothing. I don't have to copy. Even if I have millions of users here, I don't need to copy them. I'm just copying a reference to a pointer. And the same at each level of the data structure. Let's continue. The catalog, I cannot point to the old catalog because I want to change it in order to update the publication year of Watchmen. So I need to create a new catalog, but the authors by ID could be the same. So again, same trick. I'm going to point, and it's cheap. It's one operation, even if there are millions of authors. Let's continue with the books. Most of the books, I can copy them. If I have a million books, I just copy them, just the reference, not the data. And Watchmen, I need to create a new Watchmen with the change, but most of the fields, I can just copy them again and again and again. And recursively, you do that, and you are able to create a new version of the catalog with no performance hit. So it's both immutable and performant. And obviously, you don't need to write code for that. There are libraries that provide it. I will show you right now. So for example, in JavaScript, you have libraries like low-fp that provide structural sharing, Ramda, Immer. And there is even an ECMAScript. ECMAScript is a JavaScript standard proposal for having record and tuple, which is like immutable maps and immutable arrays. Oh, just a moment, I see a question. Oh, is this structural sharing provided by libraries? Yes, okay, thank you. In Java, you have something similar with in Project Lombok, they have this at value, and since Java 14, you have data record. But that's the naive approach. There is another approach And I'm going to tell you why it's naive. Because I lied, I cheated a bit. Let's say here, when I'm creating a new books object, let's say in my library, I have millions of books. With this approach, I would have to copy 1 million references. And copying 1 million references takes time. So in order to avoid this issue, you need special data structures, which are called persistent data structures. But we have them in every language. It started in Clojure in 2009. Clojure was the first language to implement persistent data structures, but now we have them everywhere in JavaScript, in Java, Go, C#, Python, Ruby, everywhere. Okay, now we come to the last principle, and it will at least partially answer the question about type safety. And I prefer to call it data validation. So let's see what happens if we take this approach of generic data structure to the edge. Let's go back to our function that we wrote before, simple function that receives a book and returns a string with the name of the book, the title of the book, and the was published in this year. And let's say I have a mistake in my program, and instead of providing the title, I mistyped the name of the field. I thought it was the title instead of title. What is going to happen? I will have a bug, but a weird bug. I don't have any exception, any error. I will just have a wrong string. You see here, I don't have the name of the book. I have was published in 1986. And so my program silently fails. And sometimes it happens that we discover bugs months later because nobody noticed that sometimes data is, the response is not accurate. So it's a problem. When you work with objects or custom data types, you don't have this problem because you cannot create a book with a wrong field name. The compiler won't let you mistype the name of the field. So what can we do? We can use data validation languages. For example, Json schema. So somewhere in my program, for example, in a JSON file, I will have the schema definition of a book. I would say a book is an object. It has 2 required fields, title and publication year. Title must be a string, and publication year must be an integer. And I would use a JSON schema validator library. For example, in JavaScript, there is AJV. I would parse the JSON schema into a programmatic representation of the schema just by parsing the file. It's the regular JSON parse stuff. And then inside book info, instead of directly accessing the book fields, I first validate that the book I received comply with the book schema. And if it doesn't comply, I will throw an exception. If it complies, I can safely move on. And let's see what happens if I pass an invalid book like before. Remember, before it would silently fail and returns a wrong string. Here, if I call book info with an invalid book, I get an exception. Data should have required property title. So I have an exception, and I have explanation about why data was not compliant. And this information I can send back to my user. Let's say it was a form that was filled by front-end application and there was no form validation, or there was a bug in the form validation, and somehow the data was sent to the server with a bug in the field name. I will send back to the user HTTP response with the proper error code, 400 something, bad request, and with an explanation about what was wrong in the data. So it mitigates a bit the need for type safety, not completely. There are issues, and dynamically typed languages slowly catch up and provides more and more tooling so that you don't have to explicitly write this code, say validate everywhere. But conceptually, the problem is quite solved. Okay, before we close up, let me give you an overview of where do these ideas come from? Where did it start? So in fact, it goes back to the beginning of programming in 1958, when John McCarthy invented Lisp. And Lisp was about the main goal of Lisp was, it was not the parentheses, it was not the macros, it was a language that would make it easy or possible to manipulate lists. Back then, in 1958, the other programming language was Pascal, and Pascal was good only at manipulating numbers. In Pascal, you couldn't have a struct or a map, or you could manipulate only numbers. And John McCarthy had this great idea of allowing a program to manipulate list. So what he called back list, today we called it data. In 1981, someone wrote a beautiful paper called Values and Objects, where Bruce McLennan explains what's the difference of values and objects. And when he say object, it doesn't mean necessarily object in object-oriented programming. What it means by object is something that has a state. And value is something that is immutable. And he explains beautifully, just 3 pages, why it is so complicated to write programs that manipulate objects, and why it is so simple to write programs that manipulate values. I really encourage you to take a look at this paper. It's 3 or 4 pages, written in English, no academic word, complicated word. It's really beautiful. But all of this was not really applicable before we had the proper efficient data structures. And the root of it emerged in year 2000, when Phil Bagwell invented a data structure for ideal hash trees. His purpose was totally different than data-oriented programming, but he invented the data structures. In 2006, those 2 guys, Ben Mosley and Peter Marks, introduced the distinction between essential complexity and accidental complexity. And we mentioned it briefly a moment ago. Essential complexity is the complexity of your problem. I mean, if you need to solve a complex problem, no paradigm will help you to make the problem less complex. But sometimes you have a problem that is not so complex, and your program makes it more complex. So they suggested that we should find ways to reduce accidental complexity. And Clojure and data-oriented programming is a response to their paper. So my claim is that data-oriented programming allows us to reduce accidental complexity. And Richie in 2007 invented Clojure and leveraged the data structures from Phil Bagwell from 2000 and integrated it into the language. And it was as I said, the first implementation of persistent data structures. And then it has been ported to all languages: Scala, Java, Python, Ruby, every language. So here is a summary of what we have discussed. Data-oriented programming reduces accidental complexity of information systems. It makes the system easier to reason about, to understand, to maintain for human beings. It has nothing to do with performance. And what it does, it summarizes 4 principles well known by many industry experts. First of all, we separate between code and data. We can write our code either in FP style or OOP style, doesn't matter. Then we separate between the representation of the data and the schema of the data. And for the presentation, we prefer to use generic data structures instead of custom types. And we never, ever mutate data. We keep data immutable. And when we apply all those principles, we have systems that are much less complex. And in my book, I illustrate in much more details how to apply, why it makes sense, when it makes sense, when it doesn't make sense, what are the challenges that you encounter when you want to apply data-oriented programming in production systems. I think I'm done. I hope you enjoyed.
Great. There is one question from Sharvit. He's asking about complexity. How do we measure that we are benefiting by using data-oriented programming? Because his perspective is that manually doing schema validation actually adds complexity to the system.
Okay. So I would say I disagree. I think that even when it's done manually, it has cumbersomeness. It doesn't add complexity. The fact that, let me go back to the slide with the schema validation. I agree that this is cumbersome to have to add this on each and every function that you want to validate. I agree, but it doesn't increase complexity. It doesn't make the function harder to understand or to maintain. It's just cumbersome that, and someday what will happen is that in JavaScript or in TypeScript or instead of writing like this, you put the schema, book schema. Let me show you what I mean. So it's just a syntax problem. It's not a fundamental problem. That's what I want to say. So that has nothing to do with complexity. It's a tooling problem. Let me illustrate that. So that's the way it's currently. And in some languages, someday you will be allowed to write like this.
Okay.
For example, you can write a macro that does that. That when you write book schema, it added this. And you can add a webpack. You can create a webpack module that does that. So that's what I wanted to say. It's a tooling problem. It's not an inherent problem. It's a problem. It's painful. It's cumbersome. I agree. But it has nothing to do with complexity. It has to do with tooling. I think it's important to distinguish.
What am I trying to say? Like, if consider whoever is doing the programming or whoever is designing the system, in that case, they will have to be aware of all these things like Json schema validation, what kind of data is there. They should be aware of the data itself, what kind of data is there. So doesn't that add an overhead to it's like person who would be working on that system? In that sense,
I couldn't hear. It's very hard for me to hear you. If you can write it in the chat, it will be very helpful.
I'll
okay.
And while he writes it in the chat, if we could just go back to your presentation, Yehonathan, I had a quick question.
Sure.
The presentation has this diagram, like a tree UML diagram, I think class diagram or object diagram.
Tell me.
Yeah. In the beginning where you showed the difference between...
just a moment.
No, the one before.
Just a moment. This one?
Yes.
No, sorry. This one?
Yes, I think so. The one after, I think, was there a diagram which actually showed data on the side? Oh yeah, here. So.
Okay, this one.
Yes. So when we made it to from object oriented to data oriented, we did not draw any lines from code to the data, right? So it may actually happen that I don't know, librarian code or book code actually.
That's for marketing reasons. So you quote me.
And it's so I think
nice
the problem. Right. And I think the problem that I see is not necessarily like it's easy to know that librarian code has to do with librarian data, but then slowly you may get like librarian code also going to catalog data and librarian data and book like.
No, but no, that's not the case. If I wanted to be totally honest, I would just need to add from here to here, from here to here. But you won't have from library code to catalog data. Never.
Okay. So if you had like, let's say catalog code had a function called catalog dot add book, like, you need to add a book inside a catalog, or you need to add.
Yes. So yeah, that's why the next step is to use generic data, and then you don't have this problem. Yeah, you're right. If you want to add a book to a catalog, you need to, in the catalog code, you need to include catalog data, and automatically you include book data in a sense. I agree with you.
Okay, got it.
Nice catch.
Thank you.
Other questions or
there is one from me.
Suggestions?
The question is about where to apply data-oriented versus the usual object-oriented approach, right? Do we apply it at a scale, or do we want to apply it at an enterprise level where correctness is more important? Or what are your thoughts regarding that?
Yeah, so the quick answer is what I call information systems, like backend or front end, and and I've been working in Clojure in projects with various scales. I don't think it matters the number of lines of code. It's applicable. It's more the kind of complexity that you want to tackle and to reduce. And you don't have to do it across the board. For example, I'm going to give you an example. Let's say you have configuration, and in your configuration object, you know exactly what are the fields that you need to have there. And there is no way to have other fields that are not specified. The configuration is created by the program, and it's not shared with any other program. So in that sense, I don't think it makes sense to use data-oriented programming to represent configuration as a generic data structure. When it makes sense is how to represent data that comes from the outside. Only there it makes sense, not everywhere. So it's fine to use struct and classes and whatever, but I think when you manipulate information that comes from the outside, whose life scope goes beyond your program, it makes sense to use data-oriented programming.
So means like in other sense, we can say like whenever there is uncertainty related to the data, means like the data can change with time or something like that. In those scenarios, this DOP might really help. Right?
Yes, and the more surprises you expect, yes, the more it's important. If you know exactly what you have and you have no surprises and you know exactly, then it's fine not to use the data-oriented programming. But if you say, okay, sometimes I have surprises and I want to be able to deal with surprises, then it makes sense.
Yes, I do agree totally with that. Thanks.
That's a nice way of putting it out there.
And I think it's part of the confusion is because it's so simple. Suddenly you say, why? I don't need this, I don't need that, I don't need classes, I don't need... So why smart people invented all of that? And there is a great quote that might provide a partial answer. There is a great quote. Let me find it, just a moment. There is a great quote by Alan Perlis about complexity and simplicity. Just a moment. Yes, this one. Simplicity does not precede complexity, but follows it. In other words, it takes time for us human beings to come up with simple solutions. So first of all, we have to expand and to tackle the problem with complex approaches like objects, types, etc. But then when we understand what it takes, we narrow back and come up with simpler and more elegant solutions.
True.
I think I was very surprised by this quote. I was very, very surprised when I discovered this quote. I think it makes sense.
Yeah, and I think SICP also suggests building programs like this, right? You build complex systems and then you build abstractions over it to make it simple to use.
Yes, exactly. So, sometimes life is easier than what we think, simpler. Sometimes no, sometimes it's difficult and you have to deal, but sometimes we just create the difficulty and the complexity. So at least in those places, let's remove it. Let's reduce it. So you can, if you want to discuss further, you can find me on Twitter and send messages. I'm quite responsive. And I'm really eager to see how you guys are going to implement and use, I don't know, maybe not all the principles, but maybe one of them that you find it useful for your day-to-day life as a programmer.
Definitely. I can already see few scenarios where we can, at least apply this data validation in like, let's say, cloud functions, which are, getting data as output and outputting.
Yes. Yeah. Great example. Great example.
Nice. Thank you very much, Yehonathan, for doing this talk. You really believe that simplicity is not easy, and this whole talk for me particularly was simple and elegant. So really enjoyed it. Gives a new perspective to how there are multiple ways of writing a program, right? And you can consider the trade-offs between them. Thank you very much again for doing the talk. And we had around 60 participants. Thank you everyone for staying till the end. We will keep doing this kind of events. Currently our goal is to do one every month. So if anybody has any recommendation for who can present next, we are open to it. Yeah, stay connected. If you want to discuss about this further, you can try to turn on a new discussion on our meetup pages. Thank you very much, everyone, for joining.
Thanks a lot. Thanks, Yehonathan.
Thank you. Thank you, Guy.